In this video, we're going to do an example of finding an eigenvalue and eigenvector for a given matrix. We're back in section 2.1 here, and we're going to let A this time be 3, 0, -1, 5. Again, we want the auxiliary matrix A minus lambda I, which I'm just going to write down here because I use it 2 or 3 times in this calculation. So our auxiliary matrix is 3 minus lambda, 0, -1, 5 minus lambda. The first thing that I want to do is find the eigenvalues by setting the determinant of this matrix equal to 0. And in this case, something kind of special happens. Well, special isn't quite right. Something convenient happens. 0 times -1 is just 0, so I could write this as 3 minus lambda times 5 minus lambda equals 0. This is already factored. So I could multiply it out, use the quadratic formula, or try to refactor it, but I'm just going to waste time doing that. Notice it's already factored, so using the zero product property of the real numbers, what we're going to get is lambda equals 3 or 5. And once again, I'm going to put a box around this in blue for eigenvalue. These are my eigenvalues. And now what I'm going to do is go one at a time to find the eigenvectors. The first up is, maybe go in increasing order or something. The first up is 3. If lambda equals 3, that means the auxiliary matrix looks like 0, 0, -1, 2. The entries of the vector v3 I'm going to call v1 and v2, and I'm interested to see which vector gets sent to the 0 vector. Well, if I just expand this out, what I get is the system of equations 0 equals 0, which tells me nothing, or -v1 plus 2v2 equals 0. In this case, this tells me that v2 equals 1/2 v1 by just pushing this over and then dividing by 2. So when I, excuse me, so when I find v sub lambda, so v3, the first entry is v1, the second entry is v2, which I'm writing as 1/2 v1, and then factoring out the v1, I get 1, the vector 1, 1/2. Now I can let v1 be any non-zero real number. Alright, well why don't I pick v1 equals 2? If I let v1 equal 2, then I get the vector 2, 1. And I have all integers, which looks sort of nice. So we'll just do that. You can leave it as 1, and then you would get 1, 1/2. No problem. Okay, for lambda equals 5, the auxiliary matrix is -2, 0, -1, 0. Oh no. The entries of the vector will be v1 and v2 again. And I still want to see what gets sent to 0, 0. But now when I write my equations out, notice what happens. I get -2 v1 equals 0 and -v1 equals 0. Both of these lead to the condition that v1 equals 0. So what do I do with this? Well, that tells me that v5 should be v1, but that's 0, v2. Okay, well I can factor out v2, and that will leave me with 0, 1. If I let v2 be anything non-zero, say 1, I get v5 equals the vector 0, 1. So to make your vectors look nice, you can pick the parameter to be whatever you want. Notice there's not really a problem if one of them gets killed. If one of them goes to 0, that's okay, because the other one is left free, and you can still do the same trick that we've been doing all along of factoring out that parameter and then just setting it equal to something convenient. In our case here, we set it equal to 1.